Section 7.2, Orthogonal Diagonalization. If A and B are square matrices, then we say that B is orthogonally similar to A if there is an orthogonal matrix P such that B equals P transpose AP. If A is orthogonally similar to some diagonal matrix, say P transpose P AP equals D, then we say that A is orthogonally diagonalizable and P orthogonally diagonalizes A. If A is an n by n matrix with real entries, then the following are equivalent. A is orthogonally diagonalizable if and only if A has an orthonormal set of n eigenvectors, if and only if A is symmetric. If A is a symmetric matrix with real entries, then the eigenvalues of A are all real numbers, and eigenvectors from different eigenspaces are orthogonal. Let's do an example and find an orthogonal matrix P that diagonalizes this matrix A that we're given. So first we'll start by finding the eigenvalues. So let's get the determinant of lambda I minus A. So that's the determinant of lambda minus 4, minus 2, minus 2, minus 2, lambda minus 4, minus 2, minus 2, minus 2, lambda minus 4. And that is equal to lambda minus 4. I'll cofactor expand it. So lambda minus 4 times this determinant, which is lambda minus 4 squared minus 4. So that's for that. Plus 2, because it's minus minus 2, times this determinant. So that's minus 2, lambda minus 4, minus 4, minus 2 for the last cofactor. So that's that determinant gives me 4 plus 2 times lambda minus 4. And that would be equal to lambda cubed minus 12 lambda squared plus 36 lambda minus 32. And let's see, in order to try to factor out a linear factor here, we need to try to come up with possible solutions, possible rational roots using the rational root theorem. So let's see, I've got possible solutions. I'll list them out. So that'll be, I take this last number divided by the first coefficient is 1. So it's just going to be all the factors of 32. So that's plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 16, and plus or minus 32. And the idea would be that you would keep dividing by these numbers, do long division until you hit one that actually works and gives you a remainder of 0. So I'll just give you a spoiler that 1 isn't going to work. It's going to be 2. I'll show you. I'll do lambda minus 2, and I'll divide lambda cubed minus 12 lambda squared plus 36 lambda minus 32. So lambda fits into lambda cubed, lambda squared times. Multiplying, we get lambda cubed minus 2 lambda squared. And then we subtract, and we get minus 10 lambda squared. And then we bring down the 36 lambda. And then we divide again. We get minus 10 lambda this time. That's how many times lambda fits in lambda squared now. So then we'll multiply again and get minus 10 lambda squared plus 20 lambda. And then subtract again, and we end up with 16 lambda, bring down 32, minus 32, and that will fit in 16 times exactly. Okay, so that means that my polynomial factors as lambda minus 2 times lambda squared minus 10 lambda plus 16. And I can factor lambda squared minus 10 lambda plus 16 much more easily as lambda minus 2 times lambda minus 8. So I'll write lambda minus 2 squared, I'll just group them together, lambda minus 8. And I'm going to set that equal to 0 to find the eigenvalues. So we can see that we have an eigenvalue of lambda equals 2 duplicated, and we have an eigenvalue of lambda equals 8. So now let's look at the equation lambda I minus a x equals 0 so that we can identify the eigenvectors. So we'll have lambda minus 4 minus 2 minus, let me move it over a little bit, minus 2 minus 2 minus 2 lambda minus 4 minus 2 minus 2 minus 2 lambda minus 4. We'll multiply that by an arbitrary vector x. I'll write it as x1, x2, x3, and set it equal to 0. So then we have to do this for lambda equals 2 and for lambda equals 8. So let's do lambda equals 2 first. So let's see, I'll set lambda equal to 2 in the equation that we just wrote, and I'll get minus 2, 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 minus 2. I'll join that 0 vector to it, and I'll solve, or I'll put this matrix in reduced row echelon form. Notice the second 2 rows are redundant. We can zero them out with the first row, divide by minus 2 just to get 1, 1, 1, 0, and then zeros throughout the rest. And now that we've reduced it, we can see that this implies that x1 plus x2 plus x3 must be equal to 0. So that means that x2 and x3 are my free variables. So I'll make those equal to some parameters t and s. So x1 is minus x2 minus x3, so it would be minus t minus s, where x2 can be t and x3 can be s. So that means that my vector x is equal to minus t minus s, t, s, and I'll separate out the t's and the s's. So this is the same thing as minus t, t 0 plus minus s 0 s, and then I'll factor out the t's and the s's. So I have t times minus 1, 1, 0, and I have s times minus 1, 0, 1. So that gives me 2 eigenvectors, u1 equal to minus 1, 1, 0, and u2 equal to minus 1, 0, 1. Not surprising we had 2 because the eigenvalue was duplicated. Now let's look, let's see. So we need to find an orthonormal basis here. We only have these guys as basis vectors, but they're not necessarily orthonormal. So in order to come up with an orthonormal basis, I'll use Gram-Schmidt process. So I'll set my first orthonormal vector v1 equal to u1, so that'll be minus 1, 1, 0. And we'll change the second one, so that'll be v2. And using our Gram-Schmidt formula, that'll be u2 minus the projection onto w1 u2, so that's u2 minus the inner product of u2 with v1 over length of v1 squared times v1, so that's minus 1, 0, 1 minus half times minus 1, 1, 0, and I'll end up with minus half, minus a half, 1. Okay, so now those are orthogonal vectors. I just need to normalize them to get orthonormal ones. So I'll make the normalized vectors with length 1 equal to the q vectors. So q1 will be v1 divided by its length. So that's minus 1 over root 2, 1 over root 2, 0. When we take v1, take the length, and divide by it. And let's get q2 now. So our vector q2 will be v2 divided by the length of v2. So that's minus 1 over root 6, minus 1 over root 6, 2 over root 6. And that takes care of my first eigenvalue. Now let's do the same thing for lambda equals 8. So it's quite a process. So we have, if we plug in lambda equals 8, remember into here we're plugging in lambda equals 8. So 8 minus 4 gives me 4, and then I've got the minus 2, 0, minus 2, 4, minus 2, 0, minus 2, 4, 0. Okay, reducing this, we divide the first row by 4, we get 1 minus half, 0. Then we add 2 of those to the second and third rows to get 0, 3, minus 3, 0, 0, minus 3, 3, 0. So we can see that the third row will cancel out, and we'll just be left with, we can, at the same time we're canceling out the third row, we can divide this row by 3 and then add it over here to cancel out that minus half, or add half of it to cancel out minus half. So we can get 1, 0, minus 1, 0 for the top row, 0, 1, minus 1, 0, and 0, 0, 0, 0 for the last row. So that gives us x1 minus x3 is equal to 0, x2 minus x3 is equal to 0, which means that we can make x3 our free variable, so we can make it a parameter, let's say t, which means x2 and x1 are both equal to t because we just move x3 to the other side. So we get that they're all equal to t. So x1 is t, x2 is t, and x3 is t. And that gives me a vector x equal to t, t, t. And I'll factor out the t. I get 1, 1, 1. And that gives me a third eigenvector u3 equal to 1, 1, 1. So I'll set that equal to the vector v3, because remember, by our theorem, we have that the eigenvectors from different eigenspaces are automatically orthogonal. So I don't have to do Gram-Schmidt. I only had to do it for the other one because I had two eigenvectors in the same eigenspace. Since v3 comes from lambda equals 8, I don't have to do Gram-Schmidt again. It's already orthogonal. So that's nice. That'll save me some time. And now I just have to normalize it to get my orthonormal vector. So that'll be v3 divided by its length. And that's just 1 over root 3, 1 over root 3, 1 over root 3. So that gives me a matrix P built out of these orthonormal vectors. So that'll be P equal to each of the Q's. Maybe I should have made each P's. It doesn't matter. So that'll be 1 over root 2, 1 over root 2, 0, minus 1 over root 6, minus 1 over root 6, 2 over root 6, 1 over root 3, 1 over root 3, and 1 over root 3. So that's my matrix P that diagonalizes A. So you could see if you tried doing the multiplication that PT AP would be equal to minus 1 over root 2, minus 1 over root 6, 1 over root 3 times 1 over root 2 minus 1 over root 6, 1 over root 3, 0, 2 over root 6, 1 over root 3 times A was 4, 2, 2, 2, 4, 2, 2, 2, 4. And I'll get 1 minus 1 over root 2. Now I'm just writing P. 1 over root 2, 0, minus 1 over root 6, minus 1 over root 6, 2 over root 6, 1 over root 3, 1 over root 3, and 1 over root 3. Multiplying out, we get 2, 0, 0, 0, 2, 0, 0, 0, 8. And it is a diagonal matrix. So it's the diagonalization of A. It's kind of nice that we actually got diagonal one. Otherwise, if it hadn't been, then yeah, who knows what would have went wrong in all those steps. If A is a symmetric matrix that is orthogonally diagonalized by P equal to U1 through UN, and if lambda 1 through lambda n are the eigenvalues of A corresponding to the unit eigenvectors U1 through UN, then A equals lambda U1, U1 transpose, plus lambda 2, U2, U2 transpose, and so on, through lambda n, UN, UN transpose, which is called a spectral decomposition of A. As an example, how about we find a spectral decomposition of the matrix A given right here? So again, we have to find a matrix P that diagonalizes A, but at least it's a little bit easier this time because we have a 2 by 2 matrix. So let's figure out that determinant of lambda I minus A. So that's lambda minus 1, minus 2, minus 2, lambda minus minus 2 is plus 2. And that's lambda squared plus lambda minus 6, which I can factor as lambda plus 3 times lambda minus 2. And I'll set that equal to 0 to find the eigenvectors. So I'll get an eigenvector lambda 1 equal, sorry, eigenvalue lambda 1 equal to minus 3, and eigenvalue lambda 2 equal to 2. And I'll use those to find the eigenvectors. So let's first look at lambda 1 minus 3. So we'll set lambda 1 equal to minus 3. Then the equation lambda I minus A becomes minus 4. We'll plug in minus 3. minus 2, 0, minus 2, minus 1, 0. And putting that in reduced row echelon form gives us 1 half 0, 0, 0, 0. The second row is just multiple of the first, so 0's out. And that gives me a top row of x1 plus half x2 equal to 0. So x2 is free, so I'll make that t. Solving for x1, I get that x1 is minus half t, and x2 is t. So now I'll write x equal to minus half t, factor out t, and have left over minus half 1. So that means that I could just multiply this entire thing by 2 so that I could avoid having the fraction. I'll multiply by minus 2, then I can avoid the minus also. Remember, this works for all possible t. So if you want, you could set t equal to minus 2t or something like that. Doesn't really matter. In any case, this is the same thing as saying that I just have all t's times 1 minus 2. Any multiple of the vector would still be an eigenvector. So I'll take x1 to be 1 minus 2. It's just a little bit easier than taking minus half 1. So then taking u1 to be that vector divided by its length. Remember, we don't have to do Gram-Schmidt because the other vector is in a different eigenspace, so it'll automatically be orthogonal. So I could just work with x1, divide that by its length, and I'll get 1 over root 5 minus 2 over root 5. So that's the first orthonormal vector. Now let's look at lambda 2, which was 2. So plugging 2 into lambda I minus a, I get 1 minus 2, 0, minus 2, 4, 0, because remember we set it equal to the 0 vector. Reduce that. We get 1 minus 2, 0 for the top row. Because the second one is just a multiple, it just becomes zeros. So I have x1 minus 2x2 is equal to 0. So x2 again is free, so that gives me x1 equal to 2t, where x2 is equal to t. So I'll have my vector x in this case equal to 2t. And I'll factor out t, and I'll get 2, 1. And that'll give me a vector x2 equal to 2, 1. Okay, so let's normalize that now. We'll take u2 equal to x2 divided by its length. And that is equal to 2 over root 5, 1 over root 5. And this gives us a spectral decomposition now because these vectors form the matrix P, right? There are u1 and u2. So now we can plug them into this formula over here. We have u1 transpose, we'll just transpose it, multiply by lambda 1, add that to lambda 2, u2 transpose. So we'll get the spectral decomposition as 1, 2, 2 minus 2 equal to lambda 1, u1 transpose plus lambda 2, u2 transpose. So in this case, lambda 1, I'm going to take minus 3. So that'll multiply by 1 over root 5 minus 2 over root 5 for u1 and transpose that. So that's 1 over root 5 minus 2 over root 5, and add that to 2 times, because the other eigenvalue was 2, and the other orthonormal vector was 2 over root 5, 1 over root 5, and then again 2 over root 5, 1 over root 5 transposed. Okay, so how about we do a little bit of the multiplication. I'll keep the minus 3 outside, and multiplying I get 1/5 minus 2/5 minus 2/5 4/5 plus 2 times 4/5 2/5 2/5 1/5. Before we move on, let's first consider what this spectral decomposition tells us about multiplication by A for various vectors. So for example, if we took the vector x equal to 1, 1, and we took A times x, then that would just be 1, 2, 2, minus 2 times 1, 1. So that would be 3, 0, if we just did the multiplication. However, this spectral decomposition says that we could also view A times x as, again, 1, 2, 2 minus 2 times 1, 1, but we could then break it down into minus 3 times 1/5 minus 2/5 minus 2/5 4/5 times 1, 1 plus 2 times 4/5 2/5 2/5 1/5 times 1, 1, which then becomes minus 3 times minus 1/5 2/5 plus 2 times 6/5 3/5. So these vectors minus 1/5 2/5 and 6/5 3/5 are the projections onto the eigenspaces of minus 3 and 2 of this vector 1, 1. Then if we scale them by the eigenvalues minus 3 and 2, we get 3/5 minus 6/5 12/5 6/5, and we add those guys up, and we get 3, 0. So it's saying that multiplying by A is the same thing as scaling down to the eigenspaces, and then, or projecting down to the eigenspaces, and then scaling by the eigenvalues, which is useful in certain contexts. Let's finish with just a couple theorems. If A is an n by n matrix with real entries and real eigenvalues, then there is an orthogonal matrix P such that P transpose AP is an upper triangular matrix of this form right over here. So if we have an n by n matrix with real entries and real eigenvalues, then we can find some orthogonal matrix P such that we'll have a whole bunch of zeros over here underneath all of the eigenvalues. And each eigenvalue is repeated according to its multiplicity. So that's Schur's theorem. We also have Hessenberg's theorem that if A is an n by n matrix with real entries, then there is an orthogonal matrix P such that P transpose AP is a matrix of this form, where entries below the entries below the diagonal are all 0. So the diagonal is not necessarily eigenvalues as it was in Schur's theorem, but this allows us to make a more general statement for different matrices. Notice that these two theorems are very useful in the case that you have a matrix that's not orthogonally diagonalizable, but you could still end up getting, in many cases, some sort of matrix that's like roughly triangular, which is pretty cool.